Welcome back, students, to our Chemistry 1510 video notes. In this video, we're going to be looking at ionization energy and electron affinity. Let's first start with the definition of ionization energy. Ionization energy is the amount of energy required to remove an electron from an atom. Now, technically, when we talk about this, if we do something like sodium, it needs to be sodium as a gas, turning into sodium ion as a gas and an electron being lost. Now, this process is going to take energy, which means the delta H for ionization energy is always going to be a positive value. Most of the time, we're going to talk about what's called the first ionization energy, which is the removal of the first electron of an element. You can remove more than one, and that section has its own trends. But we're going to look exclusively here at first ionization energy. Let's take a notice at our periodic table and recognize how atomic radius and ionization energy are correlated with one another. So, your atomic radius is decreasing. Remember, going this direction, your atomic radius is decreasing because your Z effective is increasing. So, what that means is that your outermost electron, or your valence electrons, are held tightly. So, if we look at something like fluorine, fluorine has a pretty high Z effective, at least in comparison to lithium. And because you have a high Z effective, the outermost electrons of fluorine are held more tightly. And because they're held more tightly, it's going to take more energy to remove them. And so that means a larger first ionization energy. Now, we don't really consider the noble gases when we're looking at ionization energies, because noble gases are actually kind of the goal, right? Things are going to lose or gain electrons until their electron configuration matches that of a noble gas. And there's a word for that. It's called isoelectronic. So let's write that off to the side. Isoelectronic is when two atom ions have matching electron configurations. So that's the whole goal of losing electrons, right? So lithium would lose an electron to have its electron configuration match that of helium. Fluorine, on the other hand, isn't really going to lose an electron to do that. It would have to lose actually 7 electrons to match a noble gas electron configuration of helium. So for fluorine, it's much easier to add an electron. So adding an electron is a whole nother idea that I'm going to put on pause, and we'll look at how our trend changes here, and then we'll look at adding electrons. So as we're looking at a column, your atomic radius is smaller at the top of the column. And remember that if your atomic radius is smaller, that means that your electrons are more tightly held. And if the electrons are being held on really tight to that positive nucleus, then it's going to take a heck of a lot more energy to pull off that electron. So if we look at our column of, my brain stopped working, group 1, alkali metals. So if we look at our alkali metals and we compare something like lithium with rubidium, and we start to consider their size, rubidium is much bigger and lithium is much smaller. And so rubidium, taking an electron off of that, would be like stealing candy from a baby. Whereas lithium would be like trying to steal candy from a pro football player. It's just not going to be as effective. It's going to take a lot more work. So that is your trend for ionization energy. When we look at the other direction, which is electron affinity, this is going to be the energy released when an atom gains an electron. Because the energy is being released, that means your delta H is going to be negative here, right? So this is going to be giving off energy. So certain atoms want an additional electron. So those atoms would be ones that generally form negative ions, which would be considered anions. So something like, if we kind of block off the noble gases again, your halogen family, which is right here, is going to be the column that has the greatest electron affinity. Actually, fluorine wants electrons more than anything else on the periodic table. It has the highest what's called electronegativity on the periodic table, which is another item that measures how badly an atom wants an electron. And it's on a smaller scale. It's on a scale of 0 to 4. Whereas electron affinity is something that's measurable of how much heat is released when that atom gains an electron. And with fluorine being the most electronegative element on the periodic table, the trend is as we go this way, there's an increase in electron affinity. An increase means that you're going to have the largest exothermic value. So the thing that's going to release the most heat during the course of the process. So the biggest negative number. Then, why these things are gaining and losing electrons really ends up relating to electron configuration and ionic bonding. So like we said earlier, atoms are going to gain or lose electrons to become isoelectronic, which means same electron configuration as a noble gas, right? So isoelectronic to a noble gas would mean fluorine gaining one electron now matches that of a noble gas. Then once these atoms have these charges and they're no longer atoms anymore, they're now ions, then they're going to be attracted to each other with electrostatic attraction, which is just a fancy way to say positives and negatives attract. So what's happening, for example, is if we look at sodium and we consider sodium and its electron configuration, sodium is going to give up its electron through the ionization energy process. So sodium's 3s electron is going to be removed, and sodium is now going to form a +1 ion. Notice how the electron configuration for sodium ion is the same now as a noble gas. It should be the same as neon. Then for chlorine, what chlorine is going to do is it's going to take that electron that sodium just gave up, and it's going to encompass it in its 3p orbital, which has one empty spot. And so now what we have is a sodium ion and a chloride ion that will be attracted to each other because opposites attract. Positives and negatives want to be next to one another. When they are next to one another, they form this thing called a crystal lattice. So this crystal lattice is showing you the sodium ion in gray and the chloride ion in green. And what's happening is you see negative, positive, negative, and it would just continue in this direction. And you're seeing negative, positive, negative, and then it would continue the pattern in this direction. And then you're seeing positive, negative, positive, negative, and it would continue in this direction. So this crystal lattice just builds on itself like a huge castle. And you see this alternating positive and negative, and that's how these ions sit with each other. Now those lines aren't really there, right? Those lines are really just there to show us the attraction between the two and start to show you how it makes this kind of square-like structure that builds upon itself. And the next video we'll look at a more realistic picture of what a crystal lattice looks like. As always, thank you for your attention. This is Katoni signing out.